You know, from the absolute very first day we walk into a science class, we get handed this exact blueprint for how the world works.
Right, the ultimate pursuit of absolute truth.
Exactly. We are taught to picture science as this massive, unshakable structure. You observe a fact, you lay down a brick.
You observe another fact, you lay down another brick.
Right, and eventually you build this impenetrable fortress of certainty on a solid rock foundation. But what if that entire blueprint is just a complete lie?
It is a massive shock to the system.
It really is. What if the greatness of science, like the actual engine of human progress, lies not in proving things right, but in its ruthless, terrifying vulnerability to being proven wrong?
Which is a profoundly uncomfortable thought. I mean, human beings are biologically wired to crave certainty.
We want to know the ground beneath our feet is solid.
Exactly. But the reality of scientific discovery is that it's not some safe harbor where we finally find the ultimate truth. It is an active, ongoing venture out into a perpetual storm.
And to take you out into that storm, our deep dive today focuses on a truly monumental source. It's Karl Popper's revolutionary masterwork, The Logic of Scientific Discovery.
It's a heavy one, but so worth it.
Oh, absolutely.
Yeah.
Our mission today is straightforward, but it is going to challenge you. We're going to completely dismantle your preconceived notions about how human knowledge is actually built.
We really are. We're going to strip away some very comfortable assumptions you probably didn't even know you had.
Yeah, what we're basically doing is taking you on a step-by-step unlearning process. Because before we can understand how the universe actually works, we have to look at the tools we use to perceive it.
Right. And we have to realize that the tool we trust the most, which is our own daily experience, is structurally flawed.
Okay, so let's start right there with the way our brains naturally process the world. If I ask, anyone on the street how a scientist does their job, they'll probably describe something that sounds incredibly logical.
Which is usually gathering data.
Yeah. They'll say a scientist looks at a bunch of specific events in the world, gathers the data, and then zooms out to declare a universal rule. That process actually has a formal name, right?
It does, yeah. It's called inductive logic.
Inductive logic.
Yeah, it's the idea that you can start with singular specific observations and logically build up to a universal truth.
Okay, give me an example.
Let me give you the classic historical example that philosophers just love to use. Imagine a biologist centuries ago.
Okay, I'm picturing them.
They see a white swan on a lake. Then they travel to another country. They see another white swan.
Right, making observations.
Exactly. They spend their whole life traveling the globe, and they observe 10,000 swans, and every single one of them is white.
Okay, so their brain naturally concludes, like all swans are white, and that feels like a solid scientific law based on heavy observation.
It totally feels solid, but Karl Popper looks at that and completely demolishes the logic. Because fundamentally, it does not matter how many singular observations you make. You could observe 1 million white swans.
Or 10 million.
Right. You could spend 10 lifetimes cataloging 10 million white swans. But that massive, towering pile of observations never logically justifies the universal claim that all swans are white.
Because, and let me see if I'm tracking, no matter how big your pile of data is, you haven't seen every single swan that has ever existed or ever will exist.
Precisely. You just haven't. And the very next swan you encounter could be black.
Which historically is exactly what happened, right? When Europeans traveled to Australia and saw black swans for the very first time.
Yep.
Yeah.
Their universal law was instantly dead, just shattered.
Wow. Okay.
The underlying issue here is what philosophers call the problem of induction. We have this deeply ingrained belief that the truth of universal scientific statements can be known by experience.
But Popper forces us to look closer.
Exactly. An account of an experience, like an experiment, a measurement, an observation, can only ever be a singular statement.
It's just a snapshot.
Right. A snapshot of one specific moment in time and space. So it's mathematically impossible to stretch a finite number of singular snapshots into an infinite universal law.
I mean, I see the logic, I do. But I have to push back here on behalf of everyone listening.
Go for it.
Because if I step away from the swans and just look at my actual daily life, I learn from experience every single day.
Sure you do. We all do.
Right. If I touch a hot stove twice and I get burned both times, my brain immediately induces a rule. Hot stoves burn hands.
Naturally.
So are you telling me that my brain is being logically invalid?
Yeah.
Because my burned hand would strongly disagree with you.
That is the perfect objection. Seriously. And it highlights a massive distinction we have to make today.
What's the distinction?
It's the difference between the psychology of human belief and the strict logic of scientific validity.
Okay, break that down for me.
What you're describing with the hot stove is a psychological habit.
A habit.
Yeah. Through millions of years of evolution, our nervous systems have been wired to expect regularities. It is an incredibly useful survival mechanism.
No, I don't like it burned.
Exactly. We develop a strong subjective feeling of conviction based on past experiences.
Because if I didn't have that habit, I'd basically burn my hand every single morning making coffee. So it clearly works.
It works for survival, absolutely. But Popper draws a razor-sharp line here. The logic of scientific knowledge is not concerned with empirical psychological facts.
It doesn't care about our feelings.
Nope. It doesn't care about our feelings of conviction or our biological survival habits. It is concerned exclusively with logical relations.
So wait, my absolute certainty that the stove will burn me tomorrow isn't a proven scientific law.
Not at all.
It's just a deeply ingrained psychological expectation.
Exactly. Let's take it a step further, actually. How do you logically justify that psychological expectation?
What do you mean?
If you try to argue that universal statements are based on experience, you are silently assuming that inductive inference actually works. You are trying to establish this underlying rule, a principle of induction.
Okay, so what does a principle of induction actually look like in practice?
It's essentially a hidden rule we apply to the universe. It's the belief that says, because things have behaved consistently in the past, they are absolutely guaranteed to behave the same way in the future.
Okay, that makes sense.
And for a long time, the scientific community desperately clung to this. Like the early 20th century physicist Hans Reichenbach was terrified of losing it.
Why was he terrified?
He argued that this principle of induction is the only thing that determines the truth of scientific theories. He literally said that without it, science would be indistinguishable from the fanciful and arbitrary creations of a poet's mind.
Because without it, we have no logical way to predict tomorrow based on today.
Exactly.
But Popper doesn't buy that we need it, right?
Popper doesn't just reject it. He completely proves that trying to justify this principle leads to a catastrophic logical loop.
Oh, a loop. How?
Ask yourself this. How do you prove that the principle of induction is true? It's not a math equation. You can't just prove it on a chalkboard.
Right. It's a statement about the real physical world.
So how do you prove it?
Well, I suppose I would say I know induction works because I've used it to predict things in the past, and my predictions came true.
Notice what you just did right there?
What did I do?
You are trying to prove that induction works by using an argument based on past experience. You are literally using induction to prove induction.
Oh, wow. Yeah, I'm essentially saying induction works because induction has worked.
Exactly.
That's completely circular.
It's like trying to power a lamp by plugging its own extension cord into itself.
Oh, that's a great visual. There's no external power source.
Right. If you try to base the principle of induction on experience, the logic instantly shatters. To justify your inductive principle, you would have to invent an inductive principle of a higher order.
And to justify that one,
You'd need another one, and another, stretching out into an infinite regress.
that's maddening.
The Scottish philosopher David Hume actually pointed this out centuries ago, but Popper is the one who took this realization and applied it like a sledgehammer to the very foundation of modern science.
So where does this leave us? I mean, if science isn't this clean, logical machine where we just plug in observations and crank out universal truths, how do scientists actually come up with these massive theories?
This might be the most freeing concept in Popper's entire framework. He argues that in the initial stage of science, the actual moment of discovery, there is no such thing as a logical method.
Wait, really? No logic at all?
None. There is no logical reconstruction of how a human being has a new idea. He even brings in Albert Einstein on this.
What did Einstein say?
Einstein openly admitted that there is no logical path leading to the highly universal laws of physics. They arrive purely through intuition, sparked by a deep engagement with experience.
That is incredible. So the initial spark of a scientific theory could come from a dream or like a sudden realization in the shower.
Or a completely irrational leap of imagination.
Yes.
Yes.
Oh.
But, and this is the crucial pivot, once that wild intuitive theory is formulated, the testing of it must be ruthlessly logical.
Okay, the testing is where the logic lives.
Yes. We cannot use induction to prove our theories are true. Therefore, we have to fundamentally change the game. We must stop trying to prove things right.
Okay, this feels like a massive paradigm shift.
Right.
But if we abandon the attempt to verify our theories, how do we distinguish between legitimate science and pure mythology?
That's the big question.
Like, going back to what Reichenbach feared, aren't we just equating astrophysics with astrology if neither can actually be proven true?
That specific anxiety is exactly what drove the philosophy of science in the early 20th century. How do we draw the boundary line?
Right.
Popper calls this the criterion of demarcation. How do we separate empirical science from pseudoscience, or from what philosophers call metaphysics?
Okay, before we go further, can we define metaphysics in this specific context?
Sure.
Because usually when I hear that word, I think of like healing crystals or supernatural auras.
Right, right. In the philosophical context of the time, metaphysics refers to literally any claim about reality that exists outside the realm of physical observation.
Okay, likewise.
It includes concepts like the existence of a soul, the nature of God, or any absolute unobservable essence of the universe.
Got it. Stuff you can't put in a test tube.
Exactly. Now, in the 1920s, a highly influential group of thinkers emerged in Vienna. They were known as the logical positivists.
Okay, the positivists.
This included philosophers like Moritz Schlick and Ludwig Wittgenstein. They looked at the chaos of human thought and decided they needed to clean house.
How did they want to clean it?
They wanted to completely eradicate metaphysics from serious intellectual discussion. They developed a really strict rule.
What was the rule?
Any statement that cannot be completely and conclusively verified by physical experience is essentially meaningless.
Meaningless. That's a strong word.
Very strong. To them, the word scientific meant meaningful, and meaningful strictly meant 100% verifiable by observation.
So if I make a statement like, humans possess an immortal soul, the positivists would say.
They would say, show me the soul under a microscope.
And obviously I can't.
Right. And they'd say, you can't. Then your statement isn't just wrong, it literally has no meaning, it is just noise.
Wow. They were not messing around. Wittgenstein famously argued that every meaningful proposition must be logically broken down into these elementary singular propositions of experience.
Exactly. If there's no physical method to completely verify a statement, you have to throw it in the garbage. They really thought they had created the ultimate weapon to protect science from superstition.
But based on what we just discussed about the swans and the infinite loop of induction, I have a feeling this weapon is about to backfire spectacularly.
Oh, it backfired so severely that it almost took the entirety of physics down with it.
Wait, really? Physics?
Yes. Popper looked at the positivists' strict rule of verification and pointed out a fatal flaw. We've already established that universal laws of nature like gravity or thermodynamics apply to an infinite number of cases across all of space and time.
Right, which means we can never observe every single instance of gravity happening.
Which means universal laws can never be completely verified by experience.
Oh, no.
Exactly. So if you strictly apply the positivists' rule that a statement is only meaningful if it can be completely verified, you don't just destroy metaphysics.
You destroy science.
You accidentally categorize all the fundamental laws of natural science as meaningless pseudo-statements.
That is hilarious, but also so tragic. In their obsession to be perfectly empirical and protect science, they accidentally classified the laws of physics as nonsense.
It got so extreme that Moritz Schlick, desperately trying to save his philosophy, ended up arguing that a natural law isn't actually a genuine statement at all.
What did he think it was then?
He claimed it was just a prescription, like a set of instructions for how to form statements. They basically twisted themselves into logical pretzels because they absolutely refused to let go of the idea of verification.
So Popper steps into this mess, looks at the wreckage, and realizes that the boundary line between science and nonsense cannot be about verification.
I can't be.
So what does he propose instead? What is the real boundary?
He introduces the concept that completely redefined modern science. Falsifiability.
Falsifiability.
Yes. Popper says that a theory is only part of empirical science if it is structurally capable of clashing with experience. It must be testable.
Okay.
And to be genuinely testable, it must take a risk. The form of the theory must allow us to logically deduce specific predictions. And if those predictions turn out to be false, the entire theory is falsified.
So a scientific theory isn't something that has been proven right. It's something that has stuck its neck out and dared the universe to chop it off.
That is perfectly stated. It's the art of being wrong.
I mean, I understand the logic. But psychologically, isn't that incredibly depressing?
Depressing. How so?
Why should we define human achievement by a negative? Like, we celebrate Einstein not because he might be wrong, but because we think he cracked the code. Why define our greatest scientific triumphs by their vulnerability?
Well, let's look at the alternative. What happens if a theory isn't vulnerable?
Okay, let's say it's not.
If a theory is designed so that it is compatible with every single possible observation, it feels very safe. But Popper points out that a theory that explains everything actually explains nothing.
Walk me through that. How can explaining everything mean you explain nothing? That sounds like a riddle.
Think about the kind of advice you might get from a generalized daily horoscope.
Okay, I'm with you.
It might say, you will face a challenge today, but you have the inner strength to overcome it.
Right. Classic horoscope stuff.
Now, no matter what happens to you that day, whether you miss your bus or have a fight with a friend or just struggle to open a stubborn jar of pickles, you can interpret it as fitting the prediction.
So the theory is never wrong.
Never. But precisely because it can't be wrong, it doesn't give you any specific useful information about how the physical world actually operates.
That makes a lot of sense. It's too elastic. It just stretches to fit whatever reality happens to occur.
Popper actually gives a brilliant logical example in the text. Consider the statement, it will rain or not rain here tomorrow.
Well, that statement is absolutely true. It's 100% verified. You can take that to the bank.
It is entirely verified, yes. But it is completely unfalsifiable.
Yes, there's no way to prove it wrong.
Right. There is no physical event that could prove it wrong. And because it is unfalsifiable, it is unscientific. It gives you zero empirical information about tomorrow's weather.
Right.
But contrast that with the statement, it will rain here tomorrow.
Now, that statement is taking a massive risk. It is actively prohibiting the state of not raining.
Yes. It divides the universe of possible outcomes into two camps. It points to one outcome and says, this will happen, and it points to the other and says, this will absolutely not happen.
It draws a line in the sand.
Exactly. By prohibiting certain events, the theory gains empirical content. It tells us something specific. Popper quotes the German poet Novalis here. Hypotheses are nets. Only he who casts will catch.
Only he who casts will catch.
You have to throw your net out into the dark water, fully accepting that it might come up empty or that a jagged rock might just tear it to shreds.
That fundamentally changes how I view scientists. They aren't bricklayers building a safe wall. They are risk takers.
Big time.
So, if we've moved past the illusion of induction and we're embracing the power of falsifiability, a new question pops up for me.
What's that?
If I have two competing scientific theories, and both are falsifiable, how do I choose between them? How do we mathematically measure which theory is casting a better net?
That takes us into the geometry of falsification.
Okay, geometry, I'm ready.
Popper introduces these concepts he calls degrees of testability and simplicity. Now, we often hear the phrase, the simpler theory is better, thrown around in science, right?
Right, usually is a reference to Occam's razor.
Exactly. We tend to think simpler theories are better just because they're aesthetically pleasing or, easier for our brains to comprehend.
Like an elegant equation just feels truer than a massive, clunky one?
But Popper completely rejects that aesthetic argument. He says a simpler theory is better for a strictly logical, mechanical reason.
Which is?
It has fewer parameters. In mathematical terms, it operates in lower dimensions. And because it relies on fewer parameters, it is significantly easier to falsify.
Okay, my math is a little rusty. Let's break down this geometry. What do we mean by parameters and dimensions in this context?
Let's visualize drawing shapes on a graph. Mathematically, a perfect circle is a simpler shape than an ellipse.
Why?
Because to mathematically define a specific circle on a plane, you only need 3 points. Those 3 points lock in the parameter.
Just 3 points, got it.
But an ellipse is more complex, it has more dimensions. To lock in the exact shape and orientation of an ellipse, you need 5 distinct points.
So the circle is mathematically simpler because it requires less information to perfectly define it.
Right.
How does that translate to a scientific theory being tested, though?
Imagine a scientist hypothesizing that the orbit of a newly discovered planet is a perfect circle. They have proposed a relatively simple 3-dimensional theory.
Okay.
To falsify that theory, you only need to observe 4 positions of the planet that do not fit on that specific circle. The moment you get that 4th divergent data point, the circle theory is totally dead.
Oh, I see. But if they had hypothesized the orbit was an ellipse...
Then they've proposed a 5-dimensional theory. To prove them wrong, you would need at least 6 specific observations that deunit from the predicted path.
The simpler the theory, the fewer data points it takes to destroy it.
Exactly.
Let me try an analogy here to see if I'm really grasping the mechanics.
Let's hear it.
Imagine 2 people at a firing range. The first person is a highly trained sniper. They point their rifle and say, I am going to hit the exact dead center of the bullseye on that specific target.
It's okay.
That is a highly precise, mathematically simple claim.
And incredibly easy to falsify.
Right. If the bullet hits even a quarter inch to the left, the claim is instantly proven wrong.
Yep.
But then the second person steps up with a massive shotgun, points it vaguely downrange, and says, I'm going to hit the wall at the end of the room.
Okay.
That claim is incredibly complex and covers a massive amount of physical space. It's almost impossible to prove wrong as long as they fire in the general direction.
That is a phenomenal analogy. The shotgun approach represents a highly complex theory with many parameters. It accommodates a huge range of outcomes.
Probably it's safe.
But the sniper's claim is infinitely more valuable to us because it is so vulnerable to being wrong. The sniper's claim tells us something highly specific about their skill and the weapon. The shotgun claim tells us almost nothing.
So the more a theory prohibits, the tighter the target it calls, the more it actually says about the world.
Yes.
Simplicity equals high empirical content. We don't just want theories that take risks. We want theories that put a massive target on their own backs.
Exactly. And Popper uses one of the most famous events in the history of science to illustrate this, Johannes Kepler's discovery of the laws of planetary motion.
Oh, okay.
We know now that planets move in ellipses, but Kepler didn't start there.
Did he start with the circle?
He did. Kepler initially hypothesized that the planets moved in perfect circles. It was a very simple, highly falsifiable hypothesis.
The sniper shot.
Yes. And because he had the meticulous observational data collected by Tycho Brahe, Kepler was able to test his simple hypothesis rigorously.
And obviously the data didn't fit. The planets weren't moving in perfect circles.
Right. But the failure of the circle hypothesis wasn't a defeat. It was a massive triumph of falsification.
Really? A triumph?
Because the circle theory was so cleanly and simply defined, its failure gave Kepler unequivocally clear data. The falsification showed him exactly how the data deviated from a circle, which provided the structural breadcrumbs he needed to formulate the elliptical hypothesis.
That's fascinating.
Popper argues that if Kepler had started with a vague, highly complex theory, if he had used the shotgun approach with dozens of parameters, he would have been completely lost.
Because he wouldn't have known what part of his theory was wrong. A complex theory can always be tweaked to absorb weird data.
Exactly. As Popper vividly puts it, Kepler would have been adrift in the skies, with no clear, logical way to eliminate his errors. The failure of the simple theory is what illuminated the path forward.
That is deeply inspiring. By being cleanly and clearly proven wrong, Kepler found his first real success.
It's beautiful, really.
Okay, so the ideal scientific method is to propose simple, highly testable theories that take massive risks. But as I think about the implications of this, we hit a wall that feels mathematically terrifying.
Oh, I know where you're going.
If we are constantly demanding theories that stick their necks out as far as possible, there's an unavoidable consequence.
Yes. We are about to cross into what might be the most counterintuitive, literal, face-slapping realization of this entire discussion.
This brings us to the paradox of zero probability.
Brace yourself.
Because if I'm following Popper's logic here, the absolute logical probability of any universal scientific law being true is exactly zero.
Zero. Not a tiny fraction. Not a microscopic percentage. Mathematically, zero.
I need you to walk me through the math on this because my brain is actively rejecting it right now.
Yeah.
How can the probability be zero?
We have to look at how mathematical probability works when applied to the infinite scale of the universe. A universal scientific law, like the law of gravity or thermodynamics, is not a localized rule.
Right.
It is a claim that applies to an infinite number of cases. It applies to every single atom in every single galaxy across all past, present, and future time.
Okay, so the scope is practically infinite.
Now, in an infinite universe, the number of possible physical events, the number of possible outcomes at any given millisecond, is also infinite.
Yeah.
So if you try to calculate the absolute logical probability of your specific universal law holding true everywhere, forever, without a single exception, against an infinite backdrop of other possibilities, what does that equation look like?
You are dividing a finite number of favorable human observations by an infinite number of unknown possibilities.
And mathematically, when you divide any finite number by infinity, the result approaches zero. The absolute probability of our physical laws being universally true is zero.
Okay, I'm going to stop you right there.
Okay.
I hear the math, but I am genuinely freaking out a little bit.
Yeah.
I have to fly on a commercial airplane next week.
Oh, boy.
Are you telling me that the mathematical probability of the laws of aerodynamics working tomorrow at 30,000 feet is 0? Why am I getting on the plane? Why do we build suspension bridges? Why trust anything science says if the probability of it being true is 0?
Take a breath. Seriously, this sheer panic you're feeling right now, it is exactly why we must draw a massive ironclad distinction between two concepts, probability and corroboration.
Okay. Probability and corroboration.
And this panic you just felt is the exact same trap that ensnared brilliant minds like the economist John Maynard Keynes and the physicist Hans Reichenbach.
They panic too.
They absolutely panic. They created an entire field called probability logic because they were terrified of the zero probability paradox.
They wanted to save the certainty of science.
Exactly. They realized they couldn't get 100% absolute truth, so they tried to settle for a high percentage. They theorized that as a scientific theory passes more and more tests, its logical probability increases.
Okay.
They wanted to be able to say the law of gravity is now 99.9% probable.
Which sounds incredibly reasonable to a nervous airplane passenger like me. Why is that wrong?
Because Popper proves that probability logic fundamentally misunderstands what makes a scientific theory valuable. We do not evaluate theories based on how probable they are.
I don't.
In fact, Popper argues that a theory with a high logical probability is mathematically useless to us.
How can a highly probable theory be useless? That sounds completely backward.
Think back to the weather example. It will rain or not rain tomorrow. That statement has a logical probability of 1. It is 100% probable.
Right.
But it has absolutely zero empirical content. It tells you nothing about the world. As a general rule, the more empirical information a statement contains, the more it asserts about how the universe works, the less probable it becomes. Popper quotes a brilliant proverb here. Speech is silvern, silence is golden. If you say absolutely nothing, you can never be wrong. If you want 100% probability, you are left with empty, silent tautologies.
So if we aren't evaluating theories by probability, what is the metric? Why am I trusting the airplane next week?
You are trusting the airplane because the laws of aerodynamics have an incredibly high degree of corroboration.
Corroboration.
Yes, we evaluate theories strictly on how well they have survived severe, rigorous testing. We want highly improbable theories.
We want them.
We want theories that make massive, risky, hyper-specific claims about the universe. And we respect those theories not because they are likely to be true, but because we have spent decades trying to shoot them down and we have failed.
Oh, wow. I see. Corroboration isn't a promise about the future. It's a battle record from the past.
Exactly.
The theory of aerodynamics isn't probably true tomorrow. It is a heavily scarred survivor that has withstood every single test we've thrown at it up until this exact second.
Beautifully put. Probability logic implies that we should prefer theories that are vague because vagueness is more probable. John Maynard Keynes actually fell into this trap.
Keynes did.
He argued that if a hypothesis is a mere guess, the lucky fact that it accidentally predicts a future event adds nothing to its scientific value.
That seems absurd. The whole point of science is to predict things.
Popper found it utterly absurd as well. If we don't value prediction, why go through the exhausting process of constructing theories at all? Why not just write down endless lists of singular observations?
Right.
We create bold theories precisely because we want to anticipate the world. A high degree of corroboration means the theory has predictive power, even if its ultimate absolute probability remains 0.
Okay, my anxiety about the airplane is slightly mitigated. I trust the battle record. But this discussion about probability leads us into incredibly murky waters when we look at modern physics.
Yes. Quantum mechanics.
Because while we might reject probability logic for evaluating theories, probability is heavily used inside the theories themselves. What happens when we look at the quantum realm?
This is a vital transition because in the 20th century, physics hit a wall with quantum mechanics. Scientists encountered phenomena that didn't seem to obey strict, predictable clockwork laws.
Right.
And this resulted in a massive philosophical crisis regarding how science deals with chance.
When I hear chance in quantum mechanics, I usually think of Heisenberg's uncertainty principle. The idea that at a subatomic level, the universe is just fundamentally random and unknowable.
And that is exactly the common misconception that Popper wants to dismantle. We often elevate chance to the status of an objective physical reality of the universe.
We treat randomness like a magical force.
Yes, we treat it like magic. But Popper forces us to rethink what a probability statement in physics actually represents. Often what we call chance is not a mystical property of the universe. It is simply a subjective lack of knowledge about initial conditions.
Let me try to ground that. If I roll a pair of dice on a craps table, we call the outcome chance.
Right.
But it's not actually magic. If I had a supercomputer that knew the exact weight of the dice, the velocity of my throw, the friction of the felt, the air pressure in the room, if I knew every single physical vector, every initial condition, I could perfectly calculate the outcome of the roll every single time.
Yeah.
It wouldn't be chance at all.
Exactly. The randomness is an illusion created by your ignorance of the variables. Popper differentiates between what he calls the frame conditions and the initial conditions.
What's the difference?
The frame conditions are the rules of the game. You must shake the dice in a cup, ensuring that the initial conditions are randomized and unknowable to you. The probability calculations we use in science are incredibly powerful tools for dealing with mass phenomena where we just can't know the individual initial conditions.
So where is the danger? Why is Popper worried about this?
The danger arises when scientists use probability as a metaphysical excuse to explain away anomalies. If we allow unlimited application of probability hypotheses, we effectively destroy the scientific method.
How does probability destroy science? Give me an example of how that goes wrong.
Popper outlines a scenario he calls speculative metaphysics. Let's imagine a rogue physicist who wants to abolish the law of gravity.
Abolish gravity, okay.
They propose a new theory. Gravity doesn't exist. Instead, particles just move completely randomly.
But I drop an apple, and it falls to the earth every single time. How does the rogue physicist explain that without gravity?
By using extreme statistical probability, the physicist argues that over a functionally infinite amount of time, it is statistically possible, however astronomically improbable, that particles will accidentally accumulate and move in a synchronized direction that perfectly mimics what we perceive as gravity.
Oh, come on.
They would say that the apple falling isn't a universal law, it is just a highly localized, temporary statistical fluke. And because the universe is so old, that fluke was bound to happen eventually.
That is maddening. Because the physicist isn't technically wrong about the math of infinity, but it feels like a total cheat code.
It is a cheat code, and Popper says it is fundamentally unscientific. Why? Because that theory explains absolutely everything, and therefore it is entirely unfalsifiable.
Right. If the apple falls, they say, see, the statistical fluke is continuing. If the apple suddenly floats upward, they say, see, the random particles finally shifted direction. You can never prove them wrong because any deviation is just written off as another random fluctuation.
Precisely. The moment a scientist looks at a physical event and says, it's just random chance, they have officially stopped doing science. This is where Popper introduces a critical concept, the principle of causality.
But wait, didn't we just spend an hour agreeing that we can't prove universal rules?
Yeah, right.
Saying everything in the universe has a strict cause? Sounds like another unfalsifiable metaphysical statement.
It is. And Popper acknowledges that. He doesn't introduce causality as a magical proven law of the universe. He introduces it as a methodological vow.
A vow. Like an oath a scientist takes.
Exactly. It is a fundamental rule of the game of science. A scientist must swear a methodological vow to never abandon the search for universal laws and to never give up trying to explain events causally.
So let me make sure I'm wrapping my head around this.
Yeah.
Let's look at quantum mechanics. Even if Heisenberg is ultimately right, even if the universe, at its absolute subatomic core, is fundamentally random and indeterminate, the scientist basically has to pretend it isn't, just to keep the game going.
That is a profound and entirely accurate way to frame it. Yes. The methodological vow demands that we act as if strict laws exist waiting to be discovered.
Because if we don't,
If we throw up our hands and surrender to randomness, the engine of discovery halts. We must treat probability statements in physics not as metaphysical dead ends, but as falsifiable hypotheses.
how do you falsify a probability? If the theory says an event has a 1 in a trillion chance of happening, and it happens, you haven't falsified the theory. The theory literally allowed for that 1 in a trillion chance.
That is the genius of the methodological vow. We make a strict decision to regard highly improbable events as physically ruled out.
Oh.
If a macroscopic physical effect is observed that our probability theory calculated was astronomically improbable, we don't shrug and say, wow, we witnessed a miracle statistical fluke. We say, our probability estimate was fundamentally wrong. The theory is falsified. We need to look deeper for the hidden cause.
We refuse to accept the miracle. We demand a mechanism.
Always. You never surrender to the fluke.
Okay, this has been an incredible dismantling of everything I thought I knew. All the pieces are really coming together. We've thrown out the illusion of induction.
Yeah.
We've embraced the daring vulnerability of falsifiability. We've accepted that the greatest scientific theories are mathematically 0% probable.
0%.
And we've seen that scientists must take a stubborn vow to seek causality, refusing to surrender to the void of random chance. All of this brings us to the grand finale of Popper's philosophy. We're going to paint the final, majestic, and, quite frankly, sobering picture of what human knowledge actually is.
To understand the weight of this final image, we really have to look back at the historical dream of science. Throughout history, the ultimate scientific ideal was encapsulated in the ancient Greek concept of episteme.
Which means what, exactly?
It means absolutely certain, demonstrable knowledge. We wanted science to be the bedrock of truth. We wanted to dig down through the dirt of ignorance until our shovels hit solid, unbreakable stone, and then build our civilization on top of it.
The ultimate fortress.
But Popper's ultimate realization, the final facelap, is this. The old scientific ideal of absolutely certain knowledge has proved to be an idol.
An idol, a false god we've been worshiping.
Yes. Science does not rest on solid bedrock. Every corroboration we achieve is relative. Every single statement, every law of physics we hold dear is forever tentative.
Forever. Wow.
To replace the false idol of bedrock, Popper gives us one of the most vivid, unforgettable metaphors in the philosophy of science. The structure of our scientific doctrines isn't a castle built on a stone foundation. We are building a magnificent, towering edifice, but we are building it directly over a bottomless swamp.
A swamp is uncertainty.
Yes. Think about the engineering required to build over a swamp. You have to drive massive wooden piles down into the mud to support the structure.
Okay, I see the visual.
In science, those piles are our basic observation statements, the experimental tests, the data points, the temporary consensus of the scientific community. We drive those piles down deep into the bog.
But the crucial part of the metaphor is that we never hit rock bottom.
Never. There is no absolute truth waiting at the bottom of the swamp. We drive the piles down, and we stop driving them not because we hit solid stone, but simply because we decide they're sturdy enough to hold the weight of the building for now.
We just settle for sturdy enough.
For now.
But as science progresses, as we ask deeper questions or invent more complex theories, the building gets heavier.
And when the building gets heavier, the old piles might start to sink. The foundations will groan. And when that happens, we have to drive those piles deeper, or we have to abandon them entirely and drive completely new piles into different parts of the swamp. The foundation of human knowledge is a constant, ongoing construction project. It is never finished, and it is never entirely secure.
Let me pause here, because I think we really need to address the psychological weight of what you're saying.
It's heavy.
If our best, most rigorous, most brilliant scientific minds openly admit that they are just building on tentative piles in a swamp, what does that mean for the average person? Most of us are navigating incredibly complex, stressful lives, and we are desperately seeking certainty.
Of course we are.
We look to science to be the adult in the room, to give us the final comforting answer. Is Popper's metaphor supposed to induce an existential panic?
It's natural to feel a sense of vertigo when you realize there's no bedrock, but Popper's philosophy shouldn't induce despair. If you truly grasp it, it should induce a profound sense of awe, because it reveals the true, gritty heroism of the scientific endeavor. The craving to be right, the desire to possess absolute, untouchable truth, is actually the enemy of discovery.
Because if you think you have the final answer, you stop looking. You become dogmatic.
Exactly. You stop driving the piles. What makes science the greatest tool humanity has ever created is not the possession of irrefutable truth. It is the reckless, hypercritical quest for truth.
The quest itself.
Yes, it is the willingness to constantly question our own fundamental assumptions. It is the bravery required to submit our most cherished, beautiful theories to the brutal fire of falsification, and to willingly tear down our own foundations when the data proves they are sinking.
It's the sheer courage to be wrong.
Precisely. As Popper says, we do not know. We can only guess. But our guesses are controlled by systematic, rigorous tests. Those who are unwilling to expose their ideas to the hazard of refutation do not take part in the scientific game.
What an incredible intellectual journey this has been today. Let's synthesize everything we've unpacked. We started by looking at how our brains naturally work, and we realized that induction, the comfortable idea that observing 1,000 sunrises proves the sun will rise tomorrow, is a logical myth. There is no absolute certainty to be found in experience.
We then explored how the logical positivists accidentally tried to destroy physics in their quest for ultimate verification, which led us to understand that the true dividing line between science and pseudoscience is falsifiability. A theory must actively risk being wrong to have any scientific value.
We looked at the geometry of falsification, realizing that simpler theories, like our sniper calling a hyper-specific shot, are easier to falsify, which makes them infinitely more powerful than vague, complex theories that accommodate everything.
We confronted the terrifying mathematical paradox that the absolute probability of any universal scientific law is zero, and we learned that we shouldn't seek theories that are probable. We want highly improbable theories that survive as battle-tested, corroborated survivors.
We saw that science demands a strict methodological vow, a refusal to surrender to random chance, and an endless commitment to seek causality. And finally, we dismantled the idol of absolute certainty, viewing human knowledge as a daring, endless construction project suspended over a swamp of uncertainty.
It is a dynamic system of bold guesses and unjustified anticipations, constantly tested, constantly refined, but never finally proven.
Which leaves us with a final provocative thought to mull over as we end this deep dive. We've spent the last hour dissecting the most rigorous, successful system of knowledge human beings have ever devised. And we've learned that science thrives entirely upon the humble acceptance that it might be utterly wrong at any given moment.
In fact, it only progresses because it actively tries to prove itself wrong.
So here's the question for you to take away and apply to your own life. If the greatest physicists and scientists in the world can celebrate the falsification of a cherished theory, if they can watch their life's work get torn down and view it as a triumph of discovery, why do we hold on to our own personal, political, and social beliefs with such unyielding, dogmatic certainty?
We build our personal identities on what we think is solid bedrock, and we defend those walls against any contradicting evidence like our lives depend on it.
But what if our personal observation tools are just as flawed as the biologists counting swans? What if the foundation of our fiercest arguments is just a sinking pile in a swamp? If the fundamental laws of the universe are tentative, maybe our personal dogmas should be too. Think about what we could achieve in our own lives, in our relationships, and in our society if we stopped exhausting ourselves trying to prove we are right all the time and bravely opened ourselves up to the incredible power of being proven wrong.
It is a terrifying way to live.
But as we've learned today, stepping away from the fortress of certainty and walking out into the storm isn't the end of knowledge. It's the only place where true discovery begins.